Hello everyone, welcome to the presentation. My name is Parth Vashist and I'm working as a Presidential Postdoctoral Fellow in the School of Material Science and Engineering, NTU Singapore. Today I'm going to talk about something very interesting which will give you a better perspective of what we do as a material scientist. So from my high school and my undergrads, I was always so much fascinated about light emitting materials, and that's why I continued my research in semiconducting nanomaterials. And I use these materials to build display devices, light emitting diodes, and solar cells. So in particular, if I say my research area is focused on metal halide perovskite materials, which are basically a type of semiconductor nanomaterials, and they are extremely useful for optoelectronic applications. Before we go into the details, let me give you an introduction on what perovskite is. So the first perovskite was discovered as a calcium titanium oxide mineral in Russia, and it's named after this mineralogist called Lev Perovsky. That's why we call it perovskite. So this perovskite crystal structure basically was a cubic perovskite structure where calcium was situated on the corner of cubic cell, titanium was in the middle, and the oxygen was on the center of each face. And there are several types of these oxide perovskite which comes under perovskite family, such as barium titanate, strontium titanate, calcium silicate, and all of these materials. These materials are extremely suitable for large bandgap applications, such as some scintillators and some sort of piezoelectrics and all these applications. Anyways, so my topic of interest is on perovskite, but not on oxide perovskite. My research area is focused on halide perovskite, which actually has the same structure, but we replace the oxygen to halogens such as chlorine, bromine, and iodine. And in my research topic here, we use ABX3 type of crystal structure. And I'll give you a more detail about what A, B, and X in more details, what they are. Before going, I divided my entire presentation in these different sections. So first we'll talk about the fundamental and what these perovskite materials are. And then I'll go into the perovskite nanocrystals. Then I go two-dimensional perovskite, and then we'll talk about some lead-free perovskite materials. This is all going to be very interesting. So stay tuned. Here, what ABX3 type perovskite is, as calcium titanate, it has cubic crystal structure where A is a monovalent cation such as cesium, rubidium, Ma is methylammonium, here you can see is an organic cation, and Fa is photoluminescence, which is another organic cation. So we can use inorganic cation as well as organic, such as methylammonium, formamidinium, guanidinium, all these kind of varieties. B here is divalent cations such as lead and tin. And X, as we already know now, it's chlorine, bromine, iodine, halogen. And this whole makes a perovskite crystal structure, which actually is an exciting new class of material, and it has emerged in the last 1 decade actually for solar cell and LED applications. So how do we define if a perovskite actually is in the perovskite domain, like is actually in cubic perovskite structure or orthorhombic perovskite structure? So before we can even calculate this tolerance factor, which basically just needs the ionic radii of each of these cations. So as we can see here, any material which has a tolerance factor less than 1 comes under perovskite, and if it's 0.9 to 1, it's cubic perovskite. For example, you can see here FAPBBr3 and MAPBBr3 and all these materials. And if the tolerance factor is between 0.7 and 9, it comes orthorhombic structure. It comes under this orthorhombic crystal structure. And if the tolerance factor is higher than 1, then it becomes an hexagonal and tetragonal. These are like distorted perovskite structure, not really a perovskite. So all of these materials have this tolerance factor, which can be calculated before even making these materials to estimate if these structures are going to be stable or not. So this is all about the theory of tolerance factor, but how the structure looks like in a bulk perovskite, in a bulk halide perovskite. As we can see, these cubic structures are basically connected together with edge sharing octahedra, and the center here is the cesium or methylammonium A side cation. And these material has shown promising properties in optoelectronics, and this was first used in 2009 here actually by a group in Japan, Professor Miyasaka, and he used this perovskite material as a light absorbing material in solar cell, and that material actually has gained a lot of attraction in solar cell industry. And this material has shown basically tremendous improvement in the power conversion efficiency of solar cell, which is basically the efficiency of a solar cell output by input. So here we can see that the power conversion efficiency from 2009 till 2015 has been increased from 4% to 21% almost, and the record efficiency for these solar cells are already more than 25% now. So this material has been proven to be a great source of optoelectronic material. And not only solar cell, this perovskite was also used for light emitting materials in LEDs. It's just a different structure. So basically the same material can be used for solar cell and LEDs if you use a different type of device structure. And here the electrons and hole are basically injected to the active layer of perovskite, and then they emit the light here, depending on the band gap. So this material has proven to be a promising material for light emitting as well as solar cell application. How do we prepare this material? And that's basically my favorite thing about perovskite. There are many material in research and in semiconductor industry which are useful for solar cell LEDs, but the way we make perovskite is like really straightforward and very simple solution process technique. All we need is a perovskite precursor solution in dimethyl formamide in DMF solvent. We mix all these A side cation, B side cation, such as cesium iodide, lead iodide, and then we just spin coat on a glass substrate. And if we are building a solar cell or LEDs, we need to coat some transport layer, of course. Then we spin coat at high RPM and annihilate. And as we annihilate, we get the brown, basically for iodide, we get like brown color, highly crystalline materials. And these basically are perovskite thin films. And when we do the scanning electron microscopy of these crystals, they look like really nicely crystalline, big, about 200, 400 nanometer crystals. And that's how they look. They have a lot of big grains, grain boundaries and all, but they are mostly defects free. So as we talk about defects free and defects, basically if you see a perovskite structure here, a band gap of a perovskite basically is formed from valence band and conduction band, and we can see within, for example, cesium lead bromide, the valence band is formed mostly by bromine 4p, and the conduction band is basically formed mostly by cesium here, right? So sorry, the conduction band is formed mostly by lead. So as we have these band gap tunability, it actually has a significant contribution from halogen. So as we change the bromine to chlorine and iodine, the valence band position moves significantly, and then you can actually tune the optical properties of these materials. For example, if you have the bromine, the material will have like a band gap somewhere in the green spectral region, but if you change the bromine to chlorine, it will become larger in the bluer or UV region, and the iodine will become more in the orange or orange or infrared region. And as we can just easily tune the band gap of these material by changing the halogens. Of course, we can also tune by changing the bromine B side, by tuning the lead B side, and or cesium by tuning the A side. But the most prominent effect you can see is just by changing the halogen. So this is all about the composition tuning and the material. Like if you talk about the state of art of these materials, like why they are so good actually, what properties of these materials make them different from other materials, basically make them different from other conventional semiconductors. And the answer for that is the defect tolerance. So for example, any conventional quantum dots, conventional nanoparticles, semiconductor materials, we can see here the valence band and the conduction band are usually formed by between two bonding and anti-bonding state. And because of that, the defects or the trap states are between the band gap. But in the case of perovskite here, we can see the valence and conduction bands are formed by two sets of antibonding orbitals. And because of that reason, the defects are usually resides within the band gap, or in worst case, somewhere at the shallow level. That's why they are more effective. These materials usually have higher radiative recombination channels because the defects are not between the band gap. And that make these material more efficient than conventional quantum dots or some conventional semiconductors. So what next is basically the next thing here is the dimensions. We can make these perovskite in all different dimensions. We can make 3-dimensional bulk perovskite. We can make a 0-dimensional quantum dots where we confine the material in all 3 dimensions x, y, z. We can make a 1-dimensional nanorods or nanowires. We need to confine it from 2 directions. We can make 2-dimensional nanoplates where we confine from 1 direction. And then we can also make quasi 2-dimensional perovskite. We call it RP perovskite, which is Riddleson Popper phase perovskite. So in the case of RP perovskite, basically, we need to just have combination of these 2D nanoplates connected together, and then number of these monolayers of 2D plates are separated by each other from some organic or inorganic cations. I'll talk about this quasi 2D in a bit more details in later slides. So this is all about the dimension of this perovskite. But we actually want to, if you want to have a lot of tunability, lot of flexibility, then we work on the perovskite nanocrystals. And the advantage of perovskite nanocrystal is we can have an organic, basically a shell or some ligand which are protecting the nanocrystals, giving them stability, passivating their defects, surface defects, and also changing the size and the shape of these nanoparticles. For example, if the nanocrystals are smaller in size, we will have blue emission. If they are bigger in size, we will have red emission. So we'll have a lot of flexibility if we make the nanocrystals. Just by changing the size, taking the advantage of quantum confinement, we can make all different color of nanoparticles. And just by changing the ligand here, as we can see, we can have different shapes such as cubic, spherical, rods, bricks, wires, and all these functionality basically. So that's why I'm really interested in perovskite nanocrystals, as well as in addition to the perovskite bulk structures. So here in the first detail of our work, basically what we did here, we make some perovskite nanomaterials and we tune the size of this. The way we make these perovskite is by hot injection route. In the hot injection route, for example, in this case, we were trying to make these cesium lead bromide nanocrystals. And we basically take the lead bromide precursor with some solvent, octadecene, and some ligand, which is oleic acid and olailamine. We inject the third precursor at higher temperature, such as 150 degrees C. As soon as we inject the precursor solution at higher temperature, it causes a sudden burst in the nucleation, and then the nuclei starts forming very fast at this particular temperature. And as soon as the nuclei starts forming, we basically cool down the reaction with ice bath, and it basically quench the reaction so fast that no more nuclei forms, and it basically result in more monodispersed nanoparticles. So the advantage of this method is we get the consistent size of nanocrystals throughout the reaction class basically. So you will have much monodispersed reaction and monodispersed nanoparticles, because the growth of the nanocrystals happen at the lower temperature than the nucleation, which basically allows the monodispersed formation of nanocrystals. And as we can see here clearly that these nanocrystals are highly luminescent with very sharp emission. For example, here in the green spectral region. And how we do the size tuning, we basically did the TM by changing the reaction temperature. So just by changing the hot injection temperature from 140 to 185, we can get all these three different sizes from 9 to 7 to 4 nanometer. And all these different sizes will have different emission properties. So for example, here you can see this bigger particle had 516 and smaller had 495. So you can tune the emission. And I of course made some bulk material of this as well, just to compare with the nanoparticles, and bulk was way more redshifted. And as we can see in the smallest nanocrystal, we start seeing some high energy absorption features, which basically is an indication of quantum confinement in these nanocrystals. And what we basically did, we fit it with the Bruce equation here, and then we figure out that the particle smaller than the Bohr diameter of cesium lead bromide, which is 7 nanometer, comes under the strong confinement. So we did show the tuning of confinement basically from weak confinement to the intermediate and to the strong confinement, just by changing the size of particles, which is really exciting because you can tune the size, you can play with the confinement and get different emission properties. And the transient absorption spectroscopy showed the similar thing what we showed in the absorption spectra basically, but it's just much more clear and pronounced here. The smallest nanocrystal showed high energy absorption feature, multimodal ground state bleach and all these things, and which basically defines the Venn diagram here, which basically the density of state here, which gets more and more discrete in the smaller nanocrystals compared to the large. So all in all, this in total is basically just showing the quantum confinement, showing the discrete energy levels, how nanocrystal works, and it's just a direct evidence of showing the quantum confinement in perovskite nanocrystals. The next thing is the color tunability. So as I talked about, the changing the size change the color. So as we saw in the previous slides, the color changed from green to sky blue, basically 516 to 495. But if we want to cover the entire visible spectrum, we need to take advantage of halide composition. So change from bromine to chlorine to iodine, and that's what we did here. So what we did here, we basically mixed the bromine chlorine alloy and made some cesium lead bromine chlorine, blue emission, green emission, then we add iodine and then get red and orange emission here. And that basically is the biggest advantage of these perovskite nanocrystals, that you can have the advantage of quantum confinement, but also the advantage of halide composition tuning. And that basically gives us the nanocrystals with emission over the entire visible spectrum. And these nanocrystals are so exciting, so bright, that we wanted to use them in LEDs application, of course. And just want to confirm the structural properties. The XRD basically tells us that as we go from cesium lead iodine to bromine, the nanocrystals structure basically gets more and more contracted, so the peak shifts towards the higher angle here. TM is just to give an idea of how these nanocrystal looks, and they have this cubic morphology here, very crystalline and cubic morphology. So the next thing what we did is basically we used these nanoparticles to build some light emitting diodes, and the fabrication of light emitting diode is very similar to what I showed in the earlier slide. We take the ITO coated glass, and then we have these P.PSS and poly-TPT organic hole transport material. Basically we want to transfer the holes into the nanoparticle layer, and then this TPBI is the electron transport layer, so we want to transfer the electron into the quantum dots, and when they recombine here, they emit the light. So that's what we did. The whole processing technique was really simple. It was solution process spin coating, and we just used the thermal evaporation for the electron transport layer and metal electrodes. And this is the current voltage graph of these nanoparticles, LEDs, and we can see the terminal voltage started from 2.5 to 4.56 in this region. And these all the LEDs are basically emitting blue color to red color. And this work basically demonstrates the one of the first few red LEDs in perovskite nanomaterials. So basically you can see we did precise tuning to get the emission electroluminescence from orange to deep red to deep red, and then here is the photoluminescence spectra with the electroluminescence spectra. And what we studied in this work, basically how the halide, basically there's one issue in these materials is that when the bromine iodine or chlorine bromine are together, there's a lot of halide segregation, and we basically gave the mechanism how it happens, and we investigated that in these electric field driven LEDs, the halide segregation is driven by the electric field, not by temperature or not by any other sources. And here we can see it as the AL peak basically moves. When we change the voltage from 4 volts to 10 volts, you can see all the AL peak positions move from their original value towards the 680 nanometer, and that basically shows the halide segregation here. And the reason for that, as I just explained, could be many, such as stark shift, but the stark shift would not be as significant as we saw, like it's 80 nanometer shift. The other reason here could be the growth of nanoparticles. Basically in the devices, sometimes nanocrystals fuse together and get bigger, but even if the nanocrystals get bigger, they will not shift 70 to 80 nanometer. The shift will be like just 10 nanometer maximum. So the only possible reason for that is the ion migration, which is a well-known phenomenon in perovskite materials. And why this could be happening is temperature, electric field, or mixture of both. But here we did some study to investigate whether it's happening because of temperature or electric field. And we can clearly see here, this we did this basically thin film preparation, and we heated the device from the thin film from 25 to 140, but we didn't see a significant peak shift. It's only 5 to 7 nanometer. There was no peak splitting as well. We did the same thing here. We applied the constant voltage into the device, and what we observe over time, when we apply the constant voltage, so electric field isn't changing, but at higher and higher voltage, the time it takes to move from its original position to 680 nanometer, it becomes faster and faster. So here from 2 seconds to 5 seconds, only 5 seconds and 40 seconds. However, when the voltage is slower, it takes minutes actually to do that. So that basically is a direct evidence that these ion migration, halide segregation is happening due to the electric field in these red LEDs. Of course, if we make the solution of it and we excite it with laser, with high power laser, then we might see the same effect, especially the Hawkes effect and other things. But we are talking about these particular red emitting LEDs here. And this halide ion migration mechanism is much more clearly explained in my paper in Chemistry of Materials, so you can go back to that and check the details of it. The next thing I have been working on is the triple cation perovskite nanocrystals. So what I have shown you earlier is cesium lead bromide. So cesium lead bromide is basically A side is just the cesium, but what we have discovered that when we mix the A side with cesium, methyl ammonium, and formamidinium, so we have mixture of all these three in A side, then the entire system becomes much more defects free. So the material becomes more phase pure, and also the material becomes less sensitive to the processing conditions. So the reproducibility increases a lot, and the whole system comes under the cubic structure. It doesn't degrade to the orthorhombic much faster. So the triple cation perovskite are really good for higher scalability, and they actually have the emission towards 530 nanometer, because cesium lead bromide emission is 518, 520 nanometer. And if you need to use this for display technology, for TV screen, the ideal emission we need in the green spectral region is 535. So the closer we are to 535, the better display it will make. And this material does make 530 nanometer emission. And the synthesis of this is much simpler than the other one. I mean, of course, we basically can make the cesium lead bromide also with the room temperature, but this method is really reproducible and easy to make. What we need to do, dissolve the perovskite precursor in DM, all these cations, and then we just drop cast in a toluene solution with the ligands. As soon as we drop cast, the nanocrystals form, and we basically just do the purification of nanocrystals, and we get the really emissive nanoparticles ink, and that ink is highly emissive under the UV lamp. And we can use these ink nanocrystals ink to fabricate highly efficient LEDs. And that's what we did here. And we can clearly see here these nanocrystals are very small in size. So as we go from what we did, basically we did more systematic in the study here. We changed the size of this. We changed the composition of this from 0% cesium to 15% cesium in triple cation. So we first make double cation, just formamidinium and methyl ammonium. Then we put 5% cesium, 10%, 15%. By doing that, we saw some increment in the size, 1 nanometer by extra cesium doping, and all of these materials are cubic perovskite. We can clearly see the same thing, the change in the lattice parameter as the cesium goes more into the structure, and that basically shows the successful incorporation of cesium into the perovskite structure here. And this systematic incorporation of cesium in the perovskite could be also clearly evident from this intensity of 100 and 200 plane, that these triple cation fall between the MA-FA and cesium system. That basically shows the formation of triple cation is successful. But we also had this solid state NMR, which basically gives us more insight into the structural property, and this is one of the only technique which basically can confirm whether we have successfully made cesium MA-FA within 1 nanoparticle. And we can here see that when we have 5 mole % cesium sample, we have more of the surface species of cesium. However, in 10 mole % the surface species get lesser and lesser, and 15% cesium has even less surface species. So what basically it tells us, basically in 15% sample it forms more of a pseudo-core shell structure, and 15% are the larger particles slightly. So cesium is more in the core of the nanoparticles. However, in 10 and 5%, especially 5% sample, we have more cesium rich surface, and higher cesium rich surface makes the material environmental friendly. Not just environmental friendly, higher cesium rich basically makes the material environmental stable. Sorry, that's the right word, not friendly. So it makes it more environmentally stable and also passivate the surface defects, because having inorganic shell, inorganic cesium rich surface makes the material more stable, because inorganic materials are always known to be more stable, so makes it more thermally stable, more environmentally stable. And as we can see here in photoluminescence efficiency, this is photoluminescence quantum yield, is basically the amount of photons coming out from the material to the photons we are exciting it with. We can see the 5 mole % cesium shows the highest photoluminescence quantum yield of 93%. That is basically directly correlated to the surface cesium passivation here, which was evident by solid state NMR. And then we use these nanomaterials to build the LEDs, use the similar structure I explained earlier, spin coating and spin coat perovskite. And we saw one of the lowest turn on in these materials basically. So the LEDs turned on at 2.0 volt, which is really low compared to the existing perovskite LEDs. All of these materials showed very high brightness, about basically close to 10,000 candles per meter square, and the external quantum efficiency was also highest for 5% cesium, which has more cesium on the surface, and the highest EQE, external quantum efficiency, was 7.4%. These LEDs showed great power efficiency as well, so it was about 35 luminance per watt. So all of these properties made this triple cation exciting material, and that basically just tells us the entire story what's happening. Triple cation nanomaterials, highly emissive, 5% sample, giving you the surface species and makes it more reproducible and stable perovskite materials. We recently published this work in JMCC. You're welcome to go back and check more details of it. So the next material I work is the quasi two-dimensional perovskite, which I just discussed with you in the introduction slide. So similar to the three-dimensional perovskite, as we know in three-dimensional here, as you can see the gray material here, it basically shows this gray material basically could be cesium, methylammonium, formamidinium, but we cannot put more than these materials because there is a space limitation here. Because if the size of this A site cation gets bigger and bigger, that will basically limit the properties. That will basically not allow the other cations to go in. But there's an option. What if I slice this perovskite into, like, make a slice, like you make a slice of butter or some sandwich, and if I slice it, you will have much more flexibility to put bigger cation here, and that is basically called quasi two-dimensional or layered perovskite. So you slice the 3D perovskite and put more cation in it. You can put bigger cation, and it basically gives you a lot of flexibility and functionality to tune with. So what quasi 2D perovskite is, as I explained, is layered perovskite. What the advantage of this perovskite is that, as you know, the nanomaterials have some limitation. Because of the ligand, they are more insulating, and you need to do more ligand exchange and other properties to tune with it. But with the quasi 2D, it basically has the advantage of confinement, quantum confinement, but also has the advantage of high conduction properties, such as three-dimensional perovskite, because it has much less organic cation. It has much less organic ligand compared to the nanoparticles. So quasi 2D is like a good balance between three-dimensional perovskite and nanoparticles, because you will have advantage of both, and that makes much better devices. So what basically 2D and quasi 2D is, when these perovskite octahedra monolayers, each monolayer is separated by some organic cation. For example, this butyl ammonium cation, that makes a pure 2D material. But when we stack 2 or 3 perovskite monolayers together and then separate these 2 or 3 with other 2 or 3 cation monolayers, that makes a quasi 2D. So if it's 1, that means n equal 1. If it's 2, n equal 2, and then so on. So you need to find the right balance. What n do you want? And that number of monolayers basically makes more optimized LEDs. For example, here you can see we fabricated these quasi 2D perovskite. We also call it Riddleson Popper phase perovskite, just different name of the same materials. So this Riddleson Popper perovskite is prepared as the same way as three-dimensional perovskite. The only thing we add into the perovskite solution is the ligand. And what ligand we add here is butyl ammonium bromide. As we add spin coated high RPM, we annihilate 100 degrees, and then we get these perovskite thin film, extremely thin films. Then we complete the device fabrication by thermal evaporating of metal electrode and the electron transport layer. We get this LED. As we apply the electric field, these LEDs show extremely high brightness, luminescence. And these LEDs, basically one of the highest in the literature so far. We just basically did some study here to calculate the number of monolayers, and it's not very accurate. It can never be very accurate to actually identify how many monolayers we form. But what we can see in the transmission electron microscopy here, in the last image here, you can see we are forming a lot of nanosheets, and these nanosheets, some of them are front-facing like that, and some of them are side-facing like this. So the side-facing nanosheets, I basically could find out some of them and then calculated the number of monolayers here, which are 17, and we found many of these. Some of them were 20, 24, 16, and we basically estimated the number of monolayer varied from 16 to 24. So these LEDs basically showed extremely high brightness from blue region to the red region. The basically the photoluminescence property could be tuned from deep blue 460 to red on green 700 nanometer. And these LED also show tuning by halide composition and tuning by confinement, because they are basically the nanostructured materials. So they have advantage of confinement, they have advantage of halide composition, they also have good conduction. So it's like taking a full package with all the advantage you can take. It's like really good, I really love it. And these LEDs show all these PL position peaks here with extremely narrow full width half maximum. That is great. So This is all about the device characteristic, how the devices work. Basically, you can see each LED turns on at around 4 volts. And the EQE of the blue LED, here we can see the external quantum efficiency of blue LED was 2.4 in deep blue region and 6.2 in like 487, close to sky blue region. These two numbers were the highest in the literature till last 2 months or 3 months. Actually, there was a new paper came in Nature Communication which outperformed these values, but our LEDs here did outperform the literature value from 2018 till 2020 July. So yeah, that is actually great. These LEDs are extremely efficient, one of the efficient. Even the green LED showed 10% efficiency, which is close to the existing literature values. So yeah, the quasi 2D makes a perfect system. The stability was also great. We had 75 minutes of stability in these LEDs in green spectral region. And what we found is the EQA only dropped 15% of its original value within first 30 minutes. So it's actually really promising. And these devices were not packaged, they were unpackaged. And the ambient condition, basically the humidity and air kills the transporting layer. So if you package the device, properly seal it, and then measure the stability, they will be much higher than this number. And so all of our LEDs here are basically this black graph on this CIE coordinate, CIE curve. And we can see our basically CIE triangle was 30% larger than the NTSC color triangle. NTSC color triangle is nothing but the National Television Service Committee triangle. So yeah, so the television we use always, the display technology, the display we buy, their color purity is 30% less than the color purity of our LEDs. That's what I want to say in a more general term. So yeah, it's great actually in terms of all these properties. Really promising material, really stable, and yeah, but really awesome. And we compare this with all the existing literature. We were the highest in the blue region, 2.4, 6.2. There was no LEDs in 2.4, 6.2. This 485 is, our 487 is 6.2. So we are one of the highest one. And they are highly stable, more stable than the quantum dot LEDs. The last thing, and very important, it's one of the most important thing actually, is the lead-free perovskite. So I've given a long talk here about these perovskite material, how exciting they are, how promising they are, how efficient they are, and they show really promising optoelectronic properties. But there is a biggest drawback, is one drawback in this material is having the toxic element lead. And we definitely, for longer term goal, of course, we want to understand the material property. We want to develop some devices, package them, make lead-free perovskite work. But then the long term goal is to make the perovskite and the research community eco-friendly, and also the commercialization when it comes to commercialization. So my focus was always to make some lead-free materials. And the way I did it here, I made some lead-free nanoparticles. What I did here, I basically replaced lead with some non-toxic materials such as copper. So copper is relatively much environmental friendly. What I did, replace lead with copper and made cesium copper iodide. And you can see here, the cesium copper iodide does not make perovskite structure itself, but it makes like a so-called zero-dimensional, reduced dimensional structure. It's not zero dimension as a quantum dot, it's the structure as zero dimension. Why we call it zero dimension? Because each octahedra is isolated here in this structure, and this isolation of each octahedra gives basically confine the exciton within itself, and that basically gives rise to the high exciton binding energy. High exciton binding energy gives a higher photoluminescence quantum yield and makes it extremely stable. So this material was stable in air for months actually. The photoluminescence quantum yield, the photoluminescence efficiency was much stable. And we make these two type of structure, which I'll talk more in details. Basically the difference between two is they both are iodide based materials, but the CS3CO2I5 has the zero-dimensional individual octahedra, no corner sharing. But the CsCO2I3 has like a rod kind of basically the one-dimensional space. So CsCO2I3 here gives us the CsCO2I3 here basically makes more of a 1D structure of within the crystal. So all octahedra are sharing one-dimensional, then isolation, then one-dimensional like that. It's basically a double chain of CO2I3 here, and here the isolated CO2I5. And what we have shown in this work, we have basically, this was the novel material. So we were the one who invented the nanoparticle of these materials. We have shown the crystal structure studies of this material, in-depth study, optical properties we did. We showed how thermally stable they are, because that's one of the biggest commercial deal to make these material work. because for commercial market, you need to make them thermally stable. And the reason for that is, for example, your mobile screen, how hot it gets, when you use your phone for like 10 minutes. If you play a game, it gets like really hot. So you need to have the material, the display material, which are highly stable thermally. So even if the screen gets hot, the material doesn't degrade. And eventually we showed the white emission from these materials. So let's go one by one. How we synthesize this material? We synthesize it by hot injection route. As you can see clearly, we basically use the hot injection just by changing the temperature. So we change the amount of ligand, which is octylamine, oleamine, and oleic acid. Use the copper iodide, octadecene precursor and solvent. We inject the precursor at higher temperatures, such as cesium lead bromide synthesis. What I did, I changed the reaction temperature from 110 to 160 and then get these two different shapes. So 110 makes CS3CO2I5, zero-dimensional basically nanoplates, and CS2I3 makes one-dimensional structure, more like a nanorods. You can see they are really nice nanorods here. Both of these materials have different optical properties and structural properties too. In terms of the structural properties, they both were extremely phase pure, more than 99% phase purity. And we confirmed the phase purity not only by Rietveld refinement here, but also did solid state NMR. We can see the cesium NMR, basically the CS3CO2I5 and CS2I3, both of these materials did not show any copper 2 plus peak. Because if there was a copper 2 plus material in this material, we would be seeing a lot of paramagnetic broadening, but we did not see any paramagnetic broadening in NMR. We only saw the cesium peak, relevant peak. Two sites for CS3CO2I5 and one site for CS2I3. So extremely phase pure material, high photoluminescence quantum yield, and high thermal stability, which was confirmed by this thermogravimetric analysis. So both of these materials were highly stable up to 600 degrees centigrade, which makes them really appealing for commercialization. And XPS, XPS basically was here to make sure the surface was not oxidized, and this is all copper 1 plus, no copper 2 plus. So this work we also recently published last year. Really interesting to read. If you want to go back to my paper in 2019, please go back and read. So now we come to the optical properties. So the CS3CO2I5 basically shows the emission in the blue spectral region, which is 444 nanometer. CS2I3, which is one-dimensional nanorods kind of shape, shows the emission at 560 nanometer. So this is blue and this is more yellowish, greenish yellowish. And the emission in this material, I need to point out that is not band-to-band emission. It's basically the defect emission. It's more like a self-trap exciton. So when electron gets to the conduction band, it gets to these defect straps, and then it gets basically the self-trap exciton emission formation. So the photoluminescence quantum yield we measured was 35 and 12%, but should be noted that the power we used for the laser, we had some limitation to excite the nanomaterials here. It was extremely low power, 0.20 microjoule per centimeter square. So the way researchers measure the photoluminescence quantum yield in these materials is with very high power laser, because high power laser gives you the high PLQY in these materials. So this 35 is not really 35, it's more of it's good to compare the relative photoluminescence quantum yield, but definitely the photoluminescence quantum yield, I would say, should be close to the lead-based perovskites here. So these materials show extremely high photoluminescence quantum yield. If you see the ion migration, basically in any perovskite, lead-based, let's say you have a green and red emitting perovskite, you mix them together, they will migrate together, the iodine bromine, and then form the orange emission. But the advantage of this material we are making is that there is no halide ion migration, as both are iodine-based material. One is CS3CO2I5, other is CS CO2I3. One is blue, other is yellow, and you mix them together in right ratio, 1:8. You can get a pure white light coming out of these material, and that's all we need for display technology. So if you can make a material emitting white light, it's great. That's all you need. You need a white light emitting material to display for the commercial TV screen and for display technology. And we showed that in our work. As they both are iodine-based material, there is no halide segregation, and then white emission can be achieved. And this white light is stable over months. So it's really one of the most promising things from these lead-free materials. And we are getting really close to the commercialization. That's very appealing. So that's the white light generation from it. So what I conclude from all in all here, what all we did here, we did make some cesium lead bromide with quantum confinement. We showed the weak to strong confinement in cesium-like bromide, one of the first study, basically clear evidence from transient absorption spectroscopy, Bruce equation. We also made some color tunable perovskite LEDs, blue, green, red from nanoparticles, and from there we studied the ion migration. Basically, we studied how the color instability happen in these LEDs. We gave the reason as a field-driven ion migration. We also made some more stable perovskite as a triple cation perovskite nanocrystals, and these perovskite nanocrystals are much more reproducible. I mean, all are reproducible, but they are less sensitive to the processing condition. So they are more rough and tough, I would say. You can make it even with less care and will be more reproducible, and they are highly stable. They are cesium rich surface, so makes it more environmentally stable. The next thing we did is quasi 2D perovskite for blue LEDs, especially because these blue LEDs are the record efficiency for these perovskite based LEDs. And the last but not the least and most important thing is lead-free perovskite. And we made some lead-free perovskite nanoparticles, copper-based, and then demonstrated the white light emission from these. And this is something very commercially viable. So that's all we have been doing from last 2 to 3 years, I would say. This triple cation, quasi 2D, lead-free perovskite, these 3 works are from my presidential fellowship, which was really exciting, and the background was more of literature and my PhD thesis. So yeah, it's very, very interesting. At the end, I would like to acknowledge people and the funding sources I have been involved with. So I would like to thank Professor Subodh, Professor Nirpan, Professor Tim White from NTU to support my work here, give me the facilities. I would like to thank Professor Jonathan Halpert from Victoria University of Wellington, who helped me a lot with this with these LEDs in my PhD, and also Prof. John Hanna, Ben, and the most important thing is my funding, who pays my salary, Presidential Postdoctoral Fellowship. Thank you so much, guys, for listening my talk. Thanks a lot.